Have you ever wondered why the deeper you go underwater, the more pressure you feel on your ears? Or why dams are built thicker at the bottom? That's fluid pressure in action. Hello and welcome. In this session, we are diving into the fascinating world of pressure in fluids, a concept that governs everything from water tanks to scuba diving. Let's start with the basics. Pressure is defined as the force exerted per unit area. In fluids, that is, liquids and gases, this force comes from the countless molecules moving and colliding with surfaces. And mathematically, we express this as P equals F divided by A, where P is pressure in pascals, F is force in newtons, and A is the area in square meters. The unit of pressure is the Pascal. 1 Pascal equals 1 Newton per square meter. Now, here's the interesting part. Fluid pressure doesn't act in just one direction. It acts equally in all directions at a point in a stationary fluid. That's why you feel uniform pressure around you when submerged in water. So what makes fluid pressure so unique? First, pressure in a fluid is always exerted perpendicularly to any surface it touches. That's why the walls of a water tank feel the force pushing straight out. Second, fluid pressure increases with depth. The deeper you go in a fluid, the more weight there is above you, and therefore more pressure. We quantify this increase using the formula P equals H times rho times G, where H is the depth, rho is the fluid's density, and G is the acceleration due to gravity. Here's something really cool. The pressure at a certain depth in a fluid depends only on the depth and the density, not on the shape of the container. This means water stored in a tall, narrow tube and a wide bucket, if at the same depth, will exert the same pressure. Take a look at the YouTube diagram. Notice how the water levels are equal. That's equal pressure at equal depths. Fascinating, isn't it? Now let's explore one of the most powerful principles in fluid mechanics, Pascal's law. It says pressure applied to an enclosed fluid is transmitted equally and undiminished in all directions. This is how car brakes, hydraulic jacks, and lifts work. Imagine pressing a small piston in a syringe filled with liquid. That small force gets transmitted through the liquid to a larger piston, amplifying the force. Mathematically, Pascal's law is represented as F divided by A equals F divided by A, or F equals A divided by A times F. Now, check out the diagram of a hydraulic lift. You'll see a small piston connected by a liquid to a larger piston. When you apply force to the smaller one, the pressure gets transmitted to the larger one, lifting heavy loads effortlessly. This only works because liquids are incompressible and can transmit pressure efficiently. Now that's elegant engineering backed by physics. Here's something that may surprise you. The air around you is a fluid too. Just like water, our atmosphere exerts pressure. We call this atmospheric pressure, and it's about 1 lakh pascals, or precisely 1.013 times 10 to the power 5 pascals at sea level. This pressure is what keeps us grounded, helps us breathe, and even supports weather systems. Like fluid pressure, atmospheric pressure also acts equally in all directions. It's the force pushing on you from all sides, and you don't even feel it because it's balanced inside and outside your body. When you suck air out of a straw, you reduce the pressure inside, and atmospheric pressure outside pushes the liquid up. So next time you enjoy a soft drink through a straw, remember, that's atmospheric pressure at work. Let's bring all this into real life. Hydraulic machines like car jacks use Pascal's law to lift heavy vehicles with minimal effort. A small push becomes a mighty lift. In multi-story buildings, water supply is managed by placing tanks at height so that gravity creates the pressure needed to push water down to taps. Ever used a dropper or syringe? These work because atmospheric pressure forces the liquid in once the inside air is removed. Even train brakes in older systems used vacuum brakes where the pressure difference stopped the train. And one more, try sealing a straw inside a mud pot and breaking it. The pot will break unevenly. That's because fluid pressure was trapped inside and couldn't balance. From medicine to mechanics, fluid pressure is at work everywhere. Let's solve a real-world problem using Pascal's law. Problem: a hydraulic lift has a small piston of area 0.01 meter squared and a force of 200 newtons is applied. The larger piston has an area of 0.5 meter squared. What force does the larger piston exert? Step 1. Apply Pascal's formula. F over A equals F over A. Substituting values. 200 divided by 0.01 equals F divided by 0.5. Now multiply both sides. F equals 200 divided by 0.01 times 0.5, that gives us F equals 20,000 times 0.5 equals 10,000 newtons. So, the lift outputs a force of 10,000 newtons from just 200. That's the magic of hydraulic systems. Alright, time to wrap things up. We've learned that fluid pressure increases with depth and acts equally in all directions. We saw how Pascal's law tells us that pressure in a fluid is transmitted undiminished, which is why hydraulic systems work so efficiently. We explored real-life applications, from syringes to water tanks, from car lifts to train brakes. Let's quickly recall the key formulas. P equals F divided by A. Pressure is force per unit area. P equals H times rho times G. Pressure in a liquid column. F over A equals F over A. Pascal's law in action. Physics isn't just equations, it's the invisible force behind everyday life. I hope you now feel more connected with how fluid pressure shapes our world. See you in the next session with another exciting concept from physics.